technical support staff here at Teledyne Tekmar, and I'm joined today by Tom Rohrkamper, who will be answering your questions during the presentation. For today's discussion, we've selected our current UV persulfate TOC analyzer, the Fusion, and its predecessor, the Phoenix 8000, both shown here. The topic is troubleshooting, and today we're going to focus on the basic operations that, if problematic, may cause problems with sample results, such as check standards failing either high or low, and also reproducibility issues such as unacceptable RSTs. We encourage you to be as prepared as possible in advance of having to troubleshoot a problem. And we do offer free phone support Monday through Friday during normal business hours. And we're always happy to assist you. However, being prepared may save hours of back and forth phone calls by having the cause already narrowed down when you first make the call. So take some time to be prepared for troubleshooting, and that would involve reading the manual, knowing the purpose and location of all the individual components of the system, learn how to use the diagnostic features in the software, being familiar with the sequence of operations for analyzing a sample, and always have your know your flow diagrams and have those ready to go. Okay, just a quick overview of some of the components of the Phoenix first. This is a photograph of the front of the Phoenix showing all the glassware. I just want to do a quick overview of these components. The 25 mil syringe and 7-port distribution valve, these are the devices which move liquids throughout the system, and they are operated by the syringe drive, which is shown in the cutout area on this photograph. Most of the syringe drive is on the inside of the unit, and it involves motors and sensors and electronics which operate the movement of the 7-port valve and the syringe. To the right of that, we have the IC sparger. This is a glass vessel which the purpose of this is to the sample will be injected into that first normally, and that will vent off the inorganic carbon from the sample to either be analyzed or to be vented off. The UV reactor, that's where your reaction takes place to convert carbon, which is in the sample liquid, into CO2 for detection by the CO2 detector. Now that reaction is done by the UV lamp and with an injection of sodium persulfate or ammonium persulfate. So as the CO2 from the sample is being sparged out of that vessel, some of the water is also going to come with it, or water moisture. And that's what the gas liquid separator to the right of the UV reactor is for. That's your first stage of removing that water that's coming over with the sample gas. And that works in combination with the small mist trap that you see to the right of that. From there, your sample is swept into the permeation dryer, which is not shown in this photograph, but that's on the interior of the unit under the right side cover. From there, then, the sample is swept to the corrosive scrubber to remove any halogens or other corrosives from the sample gas before it can enter into the detector, possibly causing problems. The next photograph is the front of the Fusion. The components here are very similar to the Phoenix. Several of these have been improved over the years. For example, the corrosive scrubber is a longer, narrower device now, so that the sample gas will come in contact with the copper and tin granules. We'll have more contact with that to remove even more corrosives. The IC sparger has also been redesigned to a U-shaped piece of glass with the frit built into it. Other than that, the components have a very similar function as on the Phoenix. The 25 mil syringe and 7-port distribution valve is actually the same one that's actually used on the Phoenix. First, a note about reproducibility issues. Generally, in an RSD, up to 2% for 3 sample replicates is considered acceptable in a TSC analysis for concentrations above 250 ppb. Concentrations less than that may run between 2 and 10% typically, and that's going to depend on the range of operations that you're running in, and also other variables such as the blank of the system and how well the method is actually set up. Now, some potential causes for inaccurate or inconsistent results are problems with liquid transfers, problems in the gas flow path, problems with the NDIR detector and the detector baseline signal, and issues with contamination. So those are the areas that we're going to cover today. We'll focus our attention to these 4, which can cause inaccurate or reproducibility issues with your results. We're going to start with liquid transfers. So both the Phoenix and the Fusion use 4 different liquids in the process of analyzing a sample, and those are sample water, sodium or ammonium persulfate, phosphoric acid, and DI water. Now, liquids, as I mentioned before, are transferred throughout the system through the use of the 25 ml syringe and 7-port distribution valve. The accuracy and dependency of your results, or the accuracy and reliability of your results, depends on the function of accurately transferring liquids throughout the systems. Now, liquid volumes are controlled by measuring the position of the syringe plunger as the motor moves it down, drawing in liquid. The motor stops moving the plunger at a position that correlates to a specific volume of liquid, and this operation is controlled by the syringe drive assembly, which is pictured here for both the Fusion and the Phoenix. They are very similar in how they operate. They are not interchangeable between the 2 instruments, and these are both pictured. The Fusion is on the left, and there's a connection on the top for the 7-port distribution valve and a motor directly behind it, which turns the rotor inside the 7-port distribution valve, and then below that is where the plunger from the syringe attaches. And there's a separate motor which moves the plunger of the syringe. As I said, the Phoenix on the right side of the photograph operates in much the same way. Okay, so now the syringe drive assembly, it is a very accurate, very reliable position control device. It's really extremely rare for inconsistent volumes to be caused by faulty operation of the syringe drive assembly. However, it is reasonable to assume that an inconsistent transfer could be due to a poor control of the position of the syringe. However, that is extremely rare. Problems with transfers are usually caused by a restriction or a leak somewhere in the path between the syringe and the source of the liquid, and that path includes the 7-port valve. Restrictions and leaks will result in a partial pull of the liquid, as indicated in this diagram. And what happens is that leaves a void in the syringe, part liquid, part air, and that's going to result in a low or partial injection of that liquid. Okay, so if we're having problems with our results, probably one of the first areas to look at is to observe the syringe as it's pulling in liquids during a normal sequence of running a sample. Look for an air gap while it's pulling liquids from each port. And really the only time it's going to be normal to see any kind of an air gap in the syringe is when it's draining the IC sparger and UV reactor vessels. And the software is designed to intentionally draw more than is necessary when draining those vessels, just to ensure that they are completely drained out. Now, if you do see a void in the syringe while it's pulling liquid from other places, it's either due to a restriction or a leak in that liquid pathway. So as you're observing the movement of the syringe, the way that you'll know which port is currently being pulled is on the Fusion to view the unit status window over on the far right of the main screen. Okay, and look under Mode Details and Message, and it will real-time tell you which port is currently in line with the syringe. Now, the Phoenix also displays this information in the gray bar at the bottom of the screen. However, it's a little bit trickier to determine on the Phoenix due to the fact that the message displayed on the gray bar is actually the next step in the sequence, not the current step of the sequence. Now, if you were unable to determine which port was actually in line with the syringe when you see the problem occurring in the syringe, you can also go to the Syringe Diagnostics screen. And in fact, it's before starting a long sample run, it may be a good idea to actually go into Syringe Diagnostics and just check several of the positions to make sure that they are pulling correctly. Okay, now using the Syringe Diagnostics, on the left I've just got a photograph of the 7-port valve and syringe on the Phoenix, just for reference. But to actually use the Syringe Diagnostics on the Phoenix, there is on the top part of the window, there's a valve position, so it's going to show you the current position of the 7-port valve, and then you have an option to move the position of the valve to something other than, in this example, position A. So to select a new position, just use the drop-down box, and all 7 ports will be selectable. Once you choose one, just click Move, and then the current position should change to, say, the same one that you've just selected. Now that we've got a port selected, that port will now be in line with the syringe. So in the lower half of the window, you can type in a syringe volume. Now, units of measurement is in microliters. So if you want the syringe to pull in 5 mils of liquid, you would your move to volume would be set to 5,000 or 5,000 microliters. Okay, the Fusion Diagnostics, actually it's labeled Pumper Diagnostics on the Fusion. It's a little bit easier to use, but the idea is the same. And on the 7-port valve, the ports are assigned different ports are assigned to different liquids, but they are all the same. To click into a new position or to move the valve to a new position, just click into the circle next to the port, and the valve will automatically move to that position. You don't have to click Move, in other words, to get it to go to that position. Now, operating the syringe is a matter of just simply clicking and dragging the slider bar down to a position, and the syringe will track that movement. Also, optionally, you can click on Min or Max. Min will take the syringe all the way to the top, and Max will take it all the way down to the full 25 mil. And then you could also type in a volume that you want the syringe to in the new, and that's in tenths of milliliters. And then on the Fusion, you can also set the syringe speed. Speeds 1 through 10, where 1 is very slow speed, 10 is maximum. When you change over in this area, you just want to make sure you click Move, and it will go to that position at that speed. So we want to test all the positions, especially if we're suspecting we have a problem. Now, 3 of the ports have the other end of the tube is submerged into a reservoir, and that would be your position F. The other end of that tube is submerged in the acid reservoir. G is your sodium persulfate, and H is DI water. So those are very easy to test. We just move to those positions and move the syringe down. It should be drawing in a full volume of water all the time from those positions. Again, if you see an air gap, we've got a problem with a restriction or a leak from those positions. Now, the waste position, obviously not really necessary to test pulling from the waste position. If we want to test the sample position, we would have to go to actually the auto sampler diagnostics, and the other end of this tube is connected to the auto sampler needle. So we need to go into auto sampler and move the needle to the auto sampler vial and move the needle down into a vial of DI water, and then come back to pumper diagnostics and test from that position. The two other positions are the IC sparger and UV reactor. Now those are glass vessels on the front of the fusion. So to really test from those positions, we would first have to move the valve to DI water, pull in a volume of DI water, move the valve back to IC sparger, and dispense that volume into it, and then pull back out from it to make sure it's pulling properly from that position. And the same goes with the UV reactor. Okay, so if you do see the air gap, we've either got a restriction or a leak somewhere in that pathway where we're trying to pull the liquid from. So the best way to tell whether it's a restriction or a leak is to watch what happens when the syringe stops moving. If liquid continues to drip into the syringe or slowly come into the syringe after the plunger stops moving, then we know it's a restriction, because that vacuum that's formed there is going to continue to draw in the liquid from that port. If it's a leak, there's not going to be that vacuum buildup, so it's just going to, when the plunger stops moving, there will be no more liquid come into the syringe. That's a good way of telling leak versus restriction. Okay, if we do see this problem, first area to look is, of course, all the tubing connections on the 7-port valve and also the syringe. When installing new tubing on the 7-port valve, be careful to not over-tighten the connections, as that will compress the seal that's in the port too much and actually can deform it, and that may create a restriction in that port. So when tightening tubing, thread it into the port until you feel it initially contact the bottom of the port or the seal, and then go maybe a 1/4 of an inch past there. There's really no need to tighten past that point. Now, if the fittings are not tight enough, obviously then there's going to be a port connection with that seal, and that's going to cause air to be pulled into the syringe along with the liquid. Okay, regarding the Phoenix has sparge tubes that run from the top all the way to near the bottom of each one of the vessels of the IC sparger and UV reactor. I want to make sure that those sparge tubes are not positioned too far down and up against the septa where liquids are transferred to and from the vessel. As shown on the right, that is incorrect. That sparge tube is too far down, and it's going to cause a restriction right there at the point where liquids come in and leave the vessel or drained out. So the sparge tube should actually be placed about a 1/4 of an inch above the septum at the bottom of each one of those vessels. Also regarding the Phoenix, the liquid transfer line is coming in from the bottom through a septa which has a hole in it which the transfer tubing passes through. Make sure that the transfer tubing extends all the way through that septa and is actually extending a little bit past the white Teflon backing that you see on those septas, as shown on the left. The diagram on the right is incorrect. The transfer line is placed in the middle of the septum, and that's going to create a restriction when trying to drain that vessel. In addition to that, the sample will come in contact with the rubber of the septa and actually contaminate the sample by picking up carbon from that rubber septa. Some other areas to check. Blockage or restrictions in your tubing. I would definitely recommend having spare tubing and the appropriate nuts and ferrules on hand. Probably the first thing to replace would be just replace the tubing and probably the nut and ferrule for the port where you're seeing the problem occur. So always have plenty of the extra tubing in that event that it looks like it may be restricting. Another area is the auto-sampler needle, possibly a blockage in one of the ports or through the needle. Okay, to check that, I would take the tubing off the top of the needle and submerge it in some water, and then retest from that position. If it now pulls correctly from the sample position, then we know we've got a blockage in the needle, and there's a good chance that needle may have to be replaced. Possibly the 7-port valve may have a restriction, or if that valve is starting to wear out, it may be leaking through the seals and pulling in air along with the sample. Another possibility, replacing 7-port valve. Also, look for it leaking across the syringe plunger. If you see that, the syringe needs to be replaced. You can try cleaning the syringe, however, in many cases it would have to be replaced. Okay, the next area that we're going to cover today is the gas flow path. Okay, on both the Fusion and the Phoenix, gas is sweeping CO2 from the sample into a detector which is CO2 selected. Now, the software is measuring the response of the detector and produces a carbon concentration result from CO2 which has been converted over from carbon that's in the sample. Now, obviously a leak anywhere in that flow path between the reaction vessel and the detector, a leak anywhere between those 2 points is going to cause a problem with results. You're going to get low and probably non-reproducible results as we're losing the CO2 and like the leak. So another area to look if you're seeing low and inconsistent results is to do a leak check on the system. We'll cover the Fusion first. The Fusion is equipped with a mass flow controller, or MFC, which regulates the gas flow through the sample path. Now, it controls flow. That's its primary purpose, is to control flow. However, it does monitor the gas pressure inside that sample inside the sample flow path with a transducer that's located inside the mass flow controller. So the fact that the MFC is equipped with that pressure transducer gives the Fusion the ability to perform leak checks automatically through measuring pressure drops. Okay, now on the Fusion, your first indication that there may be a leak in the sample path will be to look at your results. If we're looking at replicates collection in your report, one of the parameters that we're reporting in the report is the pressure. Okay, and that's the area highlighted in red in this example. The Fusion pressurizes the detector up to normally 50 psi, and that's a setting which is changeable in the method. So that's our target pressure. As the system pressurizes, once that pressure reaches the target pressure, or 50 in most cases, it will begin a period of stabilization. And that's usually set to about 30 seconds, but that's another parameter in the method. During the initial arriving at the target pressure and the end of the stabilization period, about 30 seconds or so, if there's a leak in the system, that pressure is going to drop off in that 30 seconds or so. So when you look at your sample results, pay attention to the pressure. If that is below your normal detector pressurization setting in the method, we may have a leak in the system. In fact, almost certainly a leak in the system. So those pressures should be at or slightly above maybe the target pressure in the method. And if so, then you can be fairly certain that the system is leak tight. However, there is a separate utility in the software for doing leak checks. And as I said earlier, it's a good practice to, before you start a long run of important samples, that go in and do a leak check on the system. Now, the leak check is part of the overall benchmark test, so not a bad idea to run a benchmark test before a sample run. Or you can go in and separately do the leak check by going to Tools, Maintenance Tasks, Leak Check. And from there you have three selections: leak check the UV flow path, leak check the IC flow path, or leak check both. Now if you select both, it doesn't check both of these paths at the same time. Sequentially, it will do one and then the other. This is the fusion flow diagram with the UV leak check pathway highlighted in red and with arrows that show the direction of flow during pressurization during a leak check. When you go into a UV leak check, it's going to set up all the valves into positions which would be exactly the same as doing a UV analysis while it's pressurizing the detector. So the vent valve, valve F, will close, and at the other end of the line we have the mass flow controller, which is controlling the gas flow into that now closed sample pathway at a rate of 300 mils per minute. Now that 300 mils per minute is the default for the leak check flow. Now that is adjustable if you go into instrument configuration. Okay, so as it's flowing 300 mils per minute into this closed pathway, naturally the pressure is going to begin to build up in the pathway. Now once that pressure reaches 50 psi, the mass flow controller is going to stop all gas flow into the system and basically shut the system off at this end. It's also still closed at the other end, so now we have a sealed system at 50 psi. Now if the pressure for some reason failed to reach 50 psi during the pressurization period, which is 5 minutes, the leak check is going to give you a failure immediately before it even completes the leak check. If the pressure does successfully reach 50 psi, the software will begin a 1-minute test where it measures the exact pressure at the end of a short equilibration time. Once that time's over, it will measure the pressure, begin the 1-minute test, measure the pressure again at the end of 1 minute. If that pressure drops less than 1 psi, your leak check passed. If leak check, or if the pressure drops more than 1 psi, leak check fails, and that will be recorded in the history events of the instrument. That's the basic operation of a leak check. The other type is the IC leak check, which is highlighted in red as well. Operates exactly the same way as the UV leak check, with the exception of the pressurization gas is routed through the IC sparger and the UV reactor is bypassed. Other than that, the leak check performs exactly the same way. Now, having two separate leak checks does help to narrow down the search for the location of the leak. For example, if our UV leak check failed and our IC leak check passed, we know that the location of the leak is either the UV reactor or something connected to the UV reactor. On the other hand, if UV leak check passed and IC leak check failed, now we know that our search should be limited to the IC sparger or something connected to the IC sparger. The other scenario is where both UV and IC leak check fail, and if they fail in approximately the same way with the same pressure delta drop, we can reason that the location of the leak must be in an area which is in common with both of those leak checks, which is highlighted in red in this example. So now that we know which area to look, the first step normally should be to go around to all the different solenoid valves and other connections in the target area that we're searching for. Just check to make sure that you have no loose fittings or any possibly a crack in one of the pieces of glassware, or maybe a piece of tubing has come loose, or possibly even been damaged by someone working on the instrument, a crack in the tube, or maybe even where that tube's been damaged in some way. So do your basic checks first, visually check all your fittings. If everything looks good with that, there are some additional tests that we can run to further narrow down the search for that leak. Okay, going back to the fusion UV leak check, a good way to start is solenoid valves. There are, in the UV leak check path, there are 5 different solenoid valves that could be suspected as being the source of the leak. And those are valve E, D, G, F, and B. Now, 3 of those valves have ports which are just vents. So those tubes are going to exit out the back of the fusion from a port just labeled vents, and they are color-coded. So the red tube is coming from valve E, blue tube from valve D, green tube is from F. So a good first test is to take those tubes that are coming from that vent port and just submerge those into some water and see if during leak check you get any bubbles out of those tubes. If so, then the valve on the other end of that tubing is leaking cross-port and needs to be replaced. The other line that we can check is the drain valve coming off of port G, and that's going to be the green drain line that you see coming from the drain port in the back. So we can also put that in some water and see if we get any bubbling from that tube. Obviously, if we do, then the drain valve is leaking and should be replaced. Another option is to plug off these ports. There is in your fusion kit box, there is a nut plug that can be inserted in place of the tubing. So you can put that plug in place, and for example, valve E, NO port, put the white plug in place of the tubing, do another leak check. If it now passes leak check, then we know that valve E is the culprit and leaking. Some other techniques are to block off different areas of the flow path during leak check. For example, the copper and tin scrubber, the corrosive scrubber, has an inlet tube and an outlet tube. If we want to isolate the leak as being either downstream of that point or upstream, we can take the tubing off of the exit side of the corrosive scrubber, put that same nut plug in place of the tubing, and perform leak check again. Obviously, if it now passes leak check, we know that something downstream is causing our leak, which would be, in this case, the detector and valve F. Don't have enough time today to go through every example of blocking things, but another technique that may be used is to bypass certain components and redo the leak check. For example, the permeation dryer is an area where leaks are somewhat common due to wear and tear of this item. So it's got an inlet and an outlet tube. To bypass the permeation dryer is really a simple matter of removing the tubing from the exit side of the permeation dryer and instead connecting it to the outlet side of the mist trap, effectively bypassing the permeation dryer. Redo the leak check, and if it now passes, then we've got a leaky permeation dryer, and that should be replaced. We could do the same thing with the mist trap. The inlet to the mist trap is the tubing that comes in from the side on the top. Disconnect that and instead connect it directly to the permeation dryer. But there are different things, and those two examples actually are easy to try because the fittings are the same between the mist trap and the permeation dryer. These are the same fittings, so it's just a simple matter of disconnecting from one and connecting to the other. Bypassing other components in the system may involve changing to a different type of nut and ferrule because there are multiple types that are used for different components. Okay, now regarding the Phoenix leak checking. Now the Phoenix doesn't have any, it's not a pressurized system, so it doesn't have a way of doing pressurized leak checks. So performing a leak check on a Fusion is a little bit more of a manual operation, and that's going to involve checking your flows at various points along the flow path. Anywhere that we check in, for example, the UV flow path, anywhere that we check in that path should be the same flow, which normally should be 200 mils per minute. So if we check our gas flow going into the UV reactor top, we should be able to measure the other end of the line, which is the vent, and be able to measure the same flow. If those flows are significantly different, then we know we're losing our sample gas somewhere in between. So step one for doing leak checking on the Phoenix is to, and this is just the another flow diagram with the UV leak check highlighted in the blue. I'll quickly go through that path. We have a gas supply which comes in through a main gas valve on or off, that's P1, and from there it's fed through another solenoid valve up to the UV reactor where it goes through that sparge tube, which disperses the bubbles into smaller bubbles, and then is routed through another valve over to the gas liquid separator, and then onto the remaining moisture removal and corrosive scrubber onto the detector. Okay, so doing a leak check on a Fusion is first going to be a matter of checking the flows, as our procedure here indicates. So step one would be to, on your gas supply, make sure that is set to 32, and that's point F in the diagram. Make sure we have correct gas pressure set from the regulator on the tank or the gas generator, whichever you're using. Okay, once we've got that set to 32, our next step is going to remove the tubing that's inserted into the sparge tube of the UV reactor. And by the way, it is a very good idea to have a handheld flow meter if you're doing troubleshooting leaks on this system. There are the onboard flow meters that you see in the software screen, and those are good, except they are subject to calibration. If you haven't calibrated the system recently or you have installed new software, those are going to default to the factory settings and really should be recalibrated. It's best to use a handheld flow meter. Okay, so we want to measure our flow going into the UV reactor by taking the tube off, measuring it. It should be 200 mils per minute. Now, if it's a little bit different than that, it's okay. The spec is actually between 180 and 220 mils per minute. Now, if it's outside of that range, it is okay to adjust the pressure regulator to achieve our 200 mils per minute. However, if you have to set that regulator above 35 psi, it's indicating a problem upstream of where the sample is coming in to the Phoenix. Possibly a defective regulator, possibly a restriction somewhere, or a leak that's upstream of that. So 35, higher than that, indicates a problem. Okay, so if we can verify we've got correct flow going to the UV reactor, reinstall the tubing on that sparge tube and go to point B and measure your flow from the vent. That should also be 200 mils per minute. And if it is, your system is leak tight, particularly if it's in the UV, if you're doing a TOC analysis. The UV path is leak tight. Okay, also on the Phoenix, there's a very good visual indicator of when your flows and pressures are correct, and that's point G on this diagram. That's your gas liquid separator. Now, the gas liquid separator has two diameters of glass which are open at the bottom. The inner diameter, which is what G is pointing to in this case, that inside diameter is open to the outside diameter. Okay, and this is a water removal device, and for it to work properly, the water must be pushed down to about 1 to 2 inches from the bottom of the vessel. So its main purpose is to remove water, but it's also a very good indicator of leaks in the system. If the inner level is higher than 2 inches, there's a good chance that we are losing gas flow somewhere in the sample path, and that's going to create a lower pressure in the sample pathway, allowing the water in that inner diameter to rise up further. If there's a abnormal restriction somewhere downstream of the gas liquid separator, that's going to cause the pressure to be too high, and that's going to force that inner water level down too far, and it may start to bubble through to the outer diameter of water or outer level. Once you see that, if it's doing a UV analysis at the time, that is gas, sample gas that we're losing out to the waste container basically, and you're going to see low results. So restriction on the Phoenix is actually just as bad as a leak. We're going to be losing our sample gas through the gas liquid separator. So as I said, normally that inner level should be 1 to 2 inches from the bottom. Okay, now if we do find that we have a leak or maybe a restriction even, the best technique here again is to try bypassing certain components, such as your permeation dryer, which is shown up in this area. The outlets of the small mist trap goes directly to the permeation dryer, and from there goes to the corrosive scrubber. So a very good way to bypass the permeation dryer is to get a different piece of tubing. It doesn't need to be too long, and then connect your top of your mist trap directly to the corrosive scrubber, the tin side, or the copper side of the corrosive scrubber. And that way we're bypassing the permeation dryer. If our flow returns to normal, once again at point B, we know that the culprit was the permeation dryer and should be replaced. Similarly, we could bypass the P4 valve, another possible source for a leak where this valve leaks where it's normally connecting COM port to NO port. If we've got leakage out to the NC port into vent, we can bypass the P4 valve. That is going to be a little bit more difficult because you will have to use a different nut and ferrule where it comes off the P4 and would connect over to the gas liquid separator. Well, you have to take the nut and ferrule off of that tubing and insert it into the gas liquid separator instead. Okay, one other area which you may find leaks would be in the UV reactor cap. Okay, so we could make a tube to bypass that as well. However, it's easier probably to go into the diagnostics, and through changing different solenoid valves, we can, instead of routing the gas into the UV and out of the UV reactor, we could route the gas instead into the IC sparger, and then from there take the normal pathway through to the vent. So to do that, you will have to go to the valve diagnostics, which is on this slide. So to set up the system for doing basically an IC analysis manually, your main gas valve, it will stay on. UV reactor valve, we want to turn that from on to off. IC sparger from off to on. And our gas output, UV gas to vent and IC gas to NDIR. Make those changes in valve diagnostics. And once you do that, your gas will now be routed in this direction instead of through the UV. Now recheck your gas flow from the vent. If you now have proper flow, we know that the problem area is in the UV reactor. Okay, so once we have determined our leak is in the UV reactor, some first things to check would be to, and this is a photograph of the top of that vessel, there's a tan-colored PEEK material cap which threads right onto the glassware, and above that there's a black round metal plate which is fastened to that tan cap. Okay, now in between the black plate and the tan cap there are 3 O-rings because there are three glass tubes that have to pass through that cap. One is your sparge tube, and the other two tubes are the UV lamp. Okay, and each one of those tubes has an O-ring which seals it from the outside. If we have verified that our leak is in the UV reactor, remove the UV reactor from the instrument, and we'll have to disassemble it and check those O-rings. You'll remove the black metal plate, and that will expose the O-rings. And while you've got it apart, whether it looks like they're needed or not, it would be a good time to just replace those O-rings. And please contact us if you need part numbers for those. On older Phoenixes, there is a different style of UV cap. If your Phoenix has a white cap, that is the older style cap, which is a Teflon material. Approximately 5 years ago, they did do an upgrade to allow this to seal, to not have a problem with leaks in the cap. So it was redesigned with a different material, which is that PEEK material, and you'll know that if you've got the tan colored cap. If you've got the old white Teflon cap and you have experienced problems with leaks in this area, it probably would be a good investment to go ahead and do that upgrade to the PEEK cap. And we do sell a kit for making that upgrade. Now, once you are reassembling the UV reactor, putting new O-rings in and reassembling it, when you're tightening that black metal plate, make sure that when you're putting the screws in and tightening the plate on, that you're drawing it down evenly. So there's two screws, tighten little by little from side to side to bring that plate down evenly on those O-rings. Okay, when it's tightened back down completely, you should be able to see a small gap between the black plate and the tan cap, and that gap should be even all the way across. The next area we're going to cover today is the NDIR detector and the detector baseline. Okay, the NDIR detector, that's non-dispersive infrared detector. Now, the detector responds to CO2, which has been converted from carbon in the sample, and the baseline is the NDIR's minimum response. So that detector should be at baseline when there's no CO2 present in the cell. Okay, so checking the baseline on the fusion. Okay, you want to make sure that the fusion's been powered up for at least 1 hour before making any determinations on whether the baseline is correct or not. It does take a certain amount of time for the electronics to warm up properly. Once that hour is up, and go ahead and put the unit into ready mode, and that's going to begin sweeping clean gas through the system, including the detector. The clean gas should contain no CO2, so the detector should go, the signal should go to baseline. On a fusion, that should be between 2 and 4 absorbance counts, which is shown in the unit status under zones as detector ABS. We're looking for between 2 and 4 absorbance counts. We're also looking for that signal to be very stable at that level. And so before running a sample schedule, it's always a good practice to go in and check the level of that baseline before running any samples. Okay, on the Phoenix, to check the baseline, go to the run screen and observe on the gray bar at the bottom of that screen a reading that's displayed as NDIR MP, and MP is for millivolts. Okay, same thing, make sure that the unit's been powered up for an hour and in ready mode for 10 minutes. After the 10 minutes, our MV should be between 0 and 50 millivolts, and preferably between 5 and 10 millivolts. And also, it should be very stable at that level. Now, if we're having problems with those baseline readings, where it's outside that specified range after 10 minutes in ready mode, before doing any other things, check to make sure that you're getting correct gas flow from the detector. In other words, we're sweeping clean gas through it before doing other things. And on the fusion, that's coming from the green tube from the vent in the back of the fusion. It's the green one. And on the Phoenix, that's coming from the gas out port in the back. If those flows are not correct at 200 mils per minute or fairly close, we have to troubleshoot a gas flow problem, not a detector problem. If still problems with the baseline, where your gas flow is correct, but still is outside that specified range, next step is to turn off the UV lamp, and you can do that by just opening the front cover of the unit. Now, if your baseline stabilizes or drops to a normal level by having the lamp turned off, there's an indication that the gas has carbon contaminants in it, and when we turned the UV lamp off, it was no longer oxidizing that carbon contamination, so we would see the signal drop off to normal. The detector does not detect carbon, just CO2. Okay, now if you turn the lamp off and there was no change, try taking the gas supply, which is connected to the back, and try connecting that directly to the detector inlet, which is pictured on the left on your Phoenix, and on the right on the NDIR detector for the Fusion, which looks quite a bit different. They are completely different styles of detectors. But connect your gas directly to the inlets, and you want to reduce the pressure because at this point there will be nothing regulating that gas flow. So reduce the pressure from the source to between 5 and 10 psi, and look at your baseline again, or your detector signal, I should say. It should be back at baseline. Now, if we see that returns properly by a direct connection, that means there's possibly CO2 contamination in the normal flow path through the instrument. Somewhere between where it normally connects and the detector, there's some CO2 contamination. Now, if there was no change in the detector signal, but it's still out of range, try a different source of gas, also connected directly to the detector inlet. If the baseline returns to normal, that means that original gas source is contaminated with CO2 and needs to be replaced. Still problems with the baseline. Gas flow is correct. You've tried 2 different sources of gas, and both of those sources of gas have been tried directly to the detector, and it's still outside of the range. Go ahead and reconnect the original source of gas to the normal gas inlet in the back of the instrument, and we'll have to adjust the baseline signal electrically on either unit. Now, on the Fusion, that's an automatic procedure, to do that, it's called Detector Offset, and you go to Tools, Maintenance Tasks, and Detector Offset. Now, we'll get a yes or no question for, are you sure you want to reset the detector baseline? Just click on yes to that, and the system will automatically electrically reset the baseline to the given level of CO2 in the cell, which should be 0, no CO2 in the cell. The procedure takes approximately 6 minutes. When it's complete, it will return the Fusion to the ready mode, and your detector absorbance count should be between 2 and 4 once that's complete. On the Fusion, adjusting the baseline is a manual operation. This is the location of the adjustment for adjusting that baseline signal. The photo on the left is a detector outside the instrument, and on the right is just to show you where that detector is located when it's installed inside the instrument, with both photos having the 0 adjustment highlighted. To actually adjust the baseline on the Phoenix, and again, power it up for at least an hour, make sure it's in ready mode for 10 minutes at least, and you're going to turn the 0 pot potentiometer into the negative or the counterclockwise direction to decrease the NDIR millivolts, and counterclockwise if you need to increase it. Okay, make sure not to set the baseline below 0. Negative numbers will not be included in the analysis if the peak is below 0. Okay, if there are still problems with the baseline, on the Phoenix, for example, the 0 knob was turned fully counterclockwise, but the baseline is still too high. That probably means that the sample cell inside the detector is dirty and needs to be cleaned. For a procedure on cleaning the sample cell, call us in technical support, and we can email you a copy of the procedure for cleaning out that sample cell. But the detector will have to be removed from the instrument and the cover removed from the detector. If you do clean the sample cell on the Phoenix and reinstall it, make sure that you readjust the 0 knob after starting the system back up. Okay, if the baseline is still not right and just going through a checklist, we've checked the gas flow from the detector and it's okay. We've tried 2 different sources of gas with both sources connected directly to the detector. We've tried adjusting the baseline, and on the Phoenix we tried cleaning the sample cell. If we still have problems with that baseline being outside of the range, on the Fusion it's an indication that possibly we've got some water has accumulated in the detector cell. If we believe that may be possible, remove the NDIR detector from the unit. It's actually very simple. There are 2 tubes to disconnect and 1 plug to disconnect, electrical plug, and then take the detector out of its bracket. Once out of the instrument, hold the detector up on its end and see if you see any water dripping out from one of the gas ports. Now, if we do see some drops of water coming out, it actually doesn't do any permanent damage to the detector, but we do have to get that dried out before we can use it again. Go ahead and drain out as much of the water as possible. After every drop has come out, then reinstall the detector back in the instrument and put the Fusion in ready mode, and that's going to start gas flowing through that detector. Now, if you don't click on the hold icon at the top of the software, it would eventually step out of ready mode and back into standby. So click on the hold icon and that will leave it in ready mode. You may have to leave it in ready mode for several hours to get that detector cell completely dried out. Once it's dry, it should return back to its normal baseline. On the Fusion, on the Phoenix, it's possibly just a bad electrical connection between the main board and the detector. Check the connections at both ends. At this point, probably be a good idea to just go ahead and replace that cable. Now, if still problems on the Fusion or Phoenix, after all the different things we've tried with the checklist above, possibly a malfunctioning main board or detector. We may have an electrical problem at this point. And the next step may be to try a main board. Hopefully we don't get to that point and we can find the problem through contaminated gas or some other cause. Okay, now the baseline signal during a sample run. Between reps, both instruments sweep pure gas through the detector to evacuate all CO2 that's from the previous sample. Now it's crucial that the detector signal returns to baseline after every rep during this sweep period. On the Fusion, that baseline is represented by the blue line in the bar graph. That is your baseline, which is not a real-time signal. That's actually updates for each bar showing what the baseline was for that particular rep. And then the different readings are just connected together with a blue line. That's not a real-time reading. And then on the right photograph, or the right diagram, is the Phoenix strip chart, which is a real-time display of the detector signal, showing in this case 3 peaks and a baseline, which is near the bottom. Okay, so on the sample results, If we're looking at a Fusion report, we can see that the baseline is one of the parameters that's updated along with all the other information given to you in the report. From this example, we had a very stable baseline. It varied from 3.02 down to 2.81, so that's considered a pretty stable baseline. And then the bar graph will show you graphically that the blue line was even all the way across. Now, the time it takes to return to that baseline can depend on the concentration of CO2 that was in the cell and the sweep flow rate. Now, remember, the Fusion is a pressurized system, so for an analysis, it's going to sweep all of the CO2 from the sample into the cell under pressure and take a one-time reading. So 100% of the CO2 from the sample is in the detector at a given time. So when that measurement is taken, a single measurement, it's very important that that CO2 that's in the cell is swept completely out. Now, if we see an inconsistent baseline, as shown in this slide, that's a very good chance that was not given enough time to evacuate the CO2 from the cell and that had accumulated from the previous wrap. And we can see that reflected in the baseline in the report. It varies from 2.77 up to 6.83. And also we saw an unacceptable RFD for that sample. And again, it's reflected here in the variation in the ppm result. Okay, there are two method parameters that are important for having that detector signal return to baseline, and those are the detector sweep flow, which is default is 500 mils per minute. Now, most of the pre-programmed methods, or I think all the pre-programmed methods, that will be set to 500. There's always a chance that someone has changed that to a lower setting somewhere along the line, and to check that, make sure it's set to 500 on your method. If it is, then the other important method parameter would be your baseline stabilization time. That's how long gas is going to flow through the detector in between reps. So if you see an inconsistent baseline, try increasing that time up to 2, maybe 3 minutes. See if the detector gets more consistent. If it does, then you can back off that setting a little bit gradually until you see the problem reoccur, and that way you'll know the correct level where it needs to be set above. Okay, the strip charts on the Phoenix. So this is on the run screen for the Phoenix. It includes that strip chart, which displays the detector signal as the red trace. Now, as I said earlier, this is a real-time display of that signal. Now, the Phoenix uses a flow-through technique for measuring CO2, not a pressurization technique. So, as part of the normal analysis, the detector is constantly being swept with 200 mils per minute of gas flow. In fact, the Phoenix will not give you a result until the signal has returned back to baseline, indicating that there's no more CO2 coming from the sample. So that's actually on the Phoenix. What triggers a result to be calculated is when that signal returns to baseline. If there are problems with returning to baseline, you would probably get a max integration time reached message, and it would be due to a tailing peak. Okay, once the peak is finished and it returns to baseline, it will generate a raw data result and calculate a ppm result. After that result's been calculated and obtained, it will continue to sweep spring gas through at 200 mils per minute, preparing the detector for the next sample. Okay, this is an example of a summary report on the Phoenix. Okay, there is some information on the reports regarding the baseline, but in the summary reports, we'd have to look at more details. So when you're looking at a Phoenix summary report, if you double-click on one of the results, it will open up and show you details on that particular sample. So now we will see the different reps and some details about those reps. And regarding the baseline, there are 3 important readings. Your beginning baseline. Oh, and by the way, if you double-click on one of the detailed results, it will open up and show you the basically the snapshot of the peak that ran for that individual peak. So if we're looking at the beginning baseline, we're looking at this area where the peak started. The ending baseline is the other side of the peak. Now those 2 numbers in your report should be fairly close. The ending baseline will always be slightly higher, and that's by design. And then the time it took to go from the beginning of the baseline to the beginning of the peak to the end of the peak is your integration time. So when we're looking at our results for the Phoenix, we want to make sure that these numbers are very consistent and that the ending baseline is fairly close, slightly above, but very close to the beginning baseline. Okay, so on a Phoenix, if it's having trouble returning the baseline, it's for a completely different reason than it is on a Fusion. On a Fusion, it was because there was not enough time to sweep the CO2 out of the cell. On a Phoenix, if we see it having trouble getting back down to the baseline, it's not due to sweep necessarily, but it indicates that the peak is having trouble coming down, or actually we're having trouble oxidizing the carbon into CO2. It's a slow reaction for some reason. And that's the kind of peak you would see if that's occurring. A peak which is broader and more tailing at the end is a sign of incomplete oxidation on the Phoenix. That can be for several reasons. It could be that the UV lamp, which is part of the oxidation process, the UV lamp may be wearing out or may be getting dimmer, and it's very dependent on that lamp to oxidize carbon into CO2. So if you see your UV lamp noticeably dimmer, or you see it begin to flicker, or even maybe change colors to more of a pinkish or purplish color, it's a good sign that UV lamp needs to be replaced. The other part of the oxidation process is the sodium persulfate, which is injected into the sample. Now, if you're running samples that are less than 1 ppm, the persulfate is not as critical. For higher concentration, it becomes very critical. And this is a classic peak that you may see if the persulfate is weak, or possibly it's not being injected into the sample properly, or it may even be a problem with the sample matrix. Is something in the sample matrix is interfering with the oxidation process, such as salt waters, such as highly chlorinated samples, samples which may be preserved with hydrochloric acid will also cause this interference to the oxidation process. Okay, so check the basics first. Make sure that and you can go back into where we talked about earlier with the liquid transfers, and make sure that it is pulling persulfate into the syringe properly, and that you're able to inject that into the sample. Possibly try changing your persulfate. And then if we suspect it may be a sample matrix interference problem, check to see if you're seeing the same type of peak when you run a standard, an unpreserved standard. If those peaks look just fine, but you're seeing problems with your sample, it's a good chance that something in that sample is interfering with that oxidation process. Okay, some other causes that can, some other areas where it may be a problem to return to baseline during an analysis, where we saw it very stable in ready mode during the running of samples, is possibly too much moisture from the samples getting into the detector. In other words, the moisture removal devices are not functioning properly. On the Phoenix, the first stage of water removal is the gas-liquid separator shown on the left. On the Fusion, your first stage is the mist trap. Now on the Fusion, the mist trap, to make sure it's operating correctly, all you really have to do is make sure that the inlet tube, which is the top port where you see the green tube coming from, that's your inlet. Make sure that that tubing extends into the vessel and by a couple of inches and is angled downwards. Also make sure that the vessel is being drained properly at the end of every sample. Not every rep, but every sample, this water level should return down to the drain line, which is the bottom port. Okay, on the Phoenix, the gas liquid separator is your first stage of water removal. Two important things here. On the inner diameter of water, make sure that that's being pushed down properly by the gas flow or the pressures in the system, as we discussed earlier. The only way that the Phoenix will remove water properly is if we're pressurizing in this area. Now, if the inner diameter is higher than this, then we've got a leak in the system, as we discussed earlier, and that leak needs to be found before we can move on. Okay, so make sure that that level is about 2 inches from the bottom. The other note on the gas liquid separator is there is a gas inlet and a gas outlet to the gas liquid separator. Make sure that the tubing on the gas inlet is extended a couple of inches into the vessel and is angled downwards. That's going to be focusing it down towards that water and pushing that water level down. If you don't extend that through and angle it downwards, your gas flow is going to take the easier path and just loop right around to the gas outlet, and very little moisture will be removed if that's the case. The secondary stage of water removal is the permeation dryer on both instruments, which is pictured here. The Fusion is a longer, narrower permeation dryer, but they operate basically the same way. And the Fusion has it coiled up. Okay, just a little bit about how the permeation dryer works. It's really a tube inside a tube. The inner tube is made of a material called Naphthalene, which easily permeates water through the walls of that tubing. It works very well, and by the way, it will not allow gas to permeate through, just water. It works very well, except that surface must be constantly swept with a drying gas, which is shown in yellow on this diagram. So we have 200 mils of drying gas coming in, sweeping across the walls of the inner tube. So as the inner tube is permeating water through, it's constantly being swept to the other end in the opposite direction and carried out to the vent. Okay, so as I said, it works very well, but if that drying gas stops for some reason, this device will no longer remove water. That material will become saturated and absolutely no water will be removed, and it's going to end up in the detector. And that's where you may have baseline issues. Now on the Fusion, there is a pressure regulator that's located very close to the permeation dryer. It's got the yellow handle on it. If you're not seeing 200 mils per minute of flow as a drying gas, possibly someone has turned the pressure regulator down and it should be readjusted. Normally you would just check your outlet drying gas, 200 mils per minute. If it's correct, our drying gas is operating properly. One other note about the permeation dryer, quite often this drying gas is used as a clean source of gas for purging out the headspace of either one of your reagent containers or the DI water container. And that's fine to do, but just make sure that the drying gas vent is not submerged in water. That can create a little bit of a restriction, and in some circumstances that water could be siphoned back into the permeation dryer, and that will ruin it. Also, if you're venting a reagent container, make sure, or purging a reagent container, make sure that that container can vent out what's being put in. The next area that we're going to cover today is contamination issues. Okay, so contamination issues, quite often when your check standards are failing on the high side, it may be due to contamination or a high system blank that's gotten worse during the course of running a sample. Okay, so now contamination is going to be in one of the following areas. It's either going to be your DI water is contaminated, the reagents are contaminated, or the instrument itself is contaminated. First about the water. This is critical because that water is used for rinsing, it's used for cleaning procedures, making dilutions, and it may be the same water that you're using to make your calibration and check standards and making the reagents. Obviously, the reagents are important because those are being injected into the sample. If the reagents are contaminated, so will the samples be. A good way to screen out where the source of the contamination is to run several cleaning procedures, or at least 2 or 3 cleaning procedures. This is an example of a schedule with some cleaning procedures on a fusion. Okay, now the results of those cleaning procedures are a very good way to gauge how clean the instrument actually is. Although the purpose of the cleaning procedure is to clean the instrument, it can give us some very good information about where our contamination is coming from. On this slide, we're looking at a typical result from one cleaning procedure. It involves 4 reps. First, there's an IC clean, and then it follows that by 3 TC clean reps. And these are typical results. First, a little bit about how the cleaning procedure works. The system will pull in DI water into the syringe and inject it into the UV reactor, and then it will treat it from there as it would a sample, and it's going to sparge it, remove or convert any carbon into CO2, and sweep it to the detector for measurement. So our TC clean results, our first one is always higher than the remaining 2 because that very first rep is the carbon that was present in the water that we're using for our cleaning procedure. Now rep 2 or rep 3, the second TC clean, is using the same water again after it has been cycled over into the IC sparger, pulled out and sent once again into the UV reactor, and takes another reading of it. Since that first rep pretty much purified the water, our second rep should be much lower than that first one. And then the third rep, it's the same thing. It cycles it back over to the IC sparger and then returns it to the UV reactor. So we can tell a lot from these results we see of the cleaning procedure. Okay, this example here, our first TC clean rep, it should be less than 15. If you have good clean water, it should be less than 15. In this example, we see where it was high. But if we look at TC clean rep 3, or the second and third TC clean, the absorbance counts came immediately down to where they should be, meaning that the system is not contaminated. In this case, it was the water which was contaminated. And the reason we say that is because of reps 3 and 4, or second and third TC clean. Okay, so if we see a result like that, try a different source of water first. Compare results. If they're the same, clean or replace the DI water reservoir. Third, replace tubing from the DI water container, the one that runs from the container to the 7-port valve. And then finally, may have to replace the 7-port valve. It could be contaminated in that port. Here's an example of a fusion clean procedure in which the first TC clean was very high and it did not come down on the second and third TC clean. This is a clear indication of instrument contamination because the second and third reps should have purified the water, but in this case, something in the pathway is recontaminating that water after it's been basically purified once. It's recontaminating the water and the counts are remaining high. A recommendation here is if you see that is to try running additional cleaning procedures. If that's not helping, some additional measures may be necessary. But run just consecutive cleanings for maybe a couple of hours and see if those counts come back down to normal. Now looking at the Phoenix, this is a Phoenix schedule with just an example with some cleaning procedures. The clean procedures are similar to the Fusions. However, you can select the number of reps to do on a clean procedure on the Phoenix where you cannot on the Fusion. We recommend to do at least 4 but no more than 6 reps for a cleaning procedure. The reason for that is cycling the water through is going to begin to heat that water up due to its contacting the UV lamp, which gets fairly hot. Okay, we don't want to heat the water up too much because that will have an adverse effect and start to strip carbon off some of the tubing, and because of the temperature of the water will actually remove carbon from the system. Okay, now very normal for our first cleaning procedure on the Phoenix is about 1 million area counts. And notice that they drop off from there, reps 2 through 6. And that again, it's using the same water for all 6 of those reps. First rep is the water. Reps 2 through 6 are from the instrument. Okay. Okay, so some additional measures if we're not seeing our cleaning reps come down to normal. Instead of cleaning with just DI water, we can clean with a 40% phosphoric acid as follows. Make a solution of 40% phosphoric acid. Take the pickup tube out of the DI water reservoir and put in that solution of phosphoric acid. Run 5 cleaning procedures with 6 reps each if it's a Phoenix, and just the normal clean procedure if it's a Fusion. Then take the tube out of the phosphoric acid and put it in a container of clean DI water. Run 5 more cleaning procedures and check your results. If that acid clean procedure is not helping, you may try repeating it several times, but it may be necessary to replace or clean some components at this point. And on the Fusion, that's going to be cleaning the glassware and syringe, and we can send you a procedure for glassware cleaning. Cleaning the UV lamp, which involves removing it and soaking it in a 5 to 10% nitric acid solution and allowing it to soak for a couple of hours. Replacing the liquid transfer tubes that run between the 7-port valve and the UV and IC vessels. Clean or replace the UV sparge tubes. Most often just replace those because they are fritted, or in the case of the Fusion, it's just the one sparge tube. But it is fritted and difficult to clean once that becomes contaminated. And then replacing the 7-port valve may be another area of contamination. On the Phoenix, very similar, except the big difference is the septas at the bottom of the IC sparge vessel and the UV reactor vessel. Those should be replaced on a regular basis anyway, but they are a source of possible contamination. The acid at some point will begin to strip the Teflon backing off of those septas, and then that is a source of contamination. But those septas should be replaced on a regular basis as part of a preventive maintenance schedule. Okay, the blank procedure. Its purpose is to measure the carbon contributed by the instrument and the reagents so that it can be subtracted from sample results. We don't want carbon that we're putting into the water to be included in the analysis, so we're going to measure it and account for it and then subtract it from your sample results. Okay, looking at a blank procedure result on the Fusion, the reagent blank, or notice that before it actually did the reagent blank measurement, it actually ran a cleaning procedure in front of it. That is for the purpose of purifying the water in which we're going to test the reagent blank. So it's purifying the water. It then injects 3 mils of persulfate into that purified water and analyzes it. Our result is shown here, in this case 4.46. That is our reagent blank, Now it will account for the volume of persulfate that you've got set in the method and do the math and subtract per mil out from your sample results. But we're looking for numbers less than 15 for your reagent blank, and for the acid blank less than 3 absorbance counts. On a Phoenix blank procedure, the first rep will always be high. On a blank procedure, you can select the number of reps, but do absolute minimum 4 reps on a blank procedure. We don't want the first rep to be included in the blank result, because the blank result is calculated from the last 3 reps of the blank procedure. Obviously, we don't want the first rep, which is naturally going to be higher, to be included in that average. Normal blank results on the Fusion, on the Phoenix blank procedure should be 50 to 100,000 counts, raw data counts. Higher than 150,000 should definitely be a concern, running a high blank. Some recommendations for high reagent or high blanks on either system is to make new persulfate or phosphoric acid. Clean or replace the persulfate or acid reservoirs. Replace the persulfate or acid tubing from the reservoir over to the 7-port valve. If that's not helping, try some new persulfate dry stock, and remember to only use the 98% purity persulfate, not the 95%. And finally, if we still can't get the blanks to come down, replace the 7-port valve. And this is all assuming that your cleaning procedure results are normal, but it's the blank results that are high. It's got to have something to do with that reagent, the persulfate primarily. Okay, testing sample blanks. If your clean procedure results and your blank procedure results are sufficiently low, but your check standards are still failing high, possibly we've got some contamination in the liquid sample path, which is the auto sampler needle, transfer line tubing from needle to 7-port valve, or the 7-port valve itself. Set up a schedule to run several DI water vials, run those as ordinary samples. We're not really concerned with the ppm result at this point. We're looking for the raw data counts on the Phoenix. We're looking at raw data counts, and on the Fusion we're looking for adjusted absorbance counts. Okay, clean DI water samples on the Fusion, you should see between 5 and 10 adjusted absorbance counts. If we're talking about a Phoenix, we should see between 100 and 200,000 raw data counts. Now, if those counts are running high, you can try running several more DI water samples from vials. If that's not helping, we can try running samples with 40% phosphoric acid instead of water to hopefully clean out that sample path from the needle to the syringe. So fill 5 vials with a solution of 40% phosphoric acid and run all 5 as ordinary samples with 3 reps each in the schedule. In the same schedule, follow that with 5 reps for 5 vials of DI water, also run as ordinary samples with 3 reps. And check your results. If those results are not decreasing, you can repeat this process. However, at this point, we may need to start replacing some parts, or at least cleaning some parts. And that's going to be on the possibly replacing first the tubing that runs from the needle over to the 7-port valve. Possibly we've got some contamination in the needle that's not washing out with the acid samples, or possibly the 7-port valve. But once we arrive at a point where the cleaning procedure results are okay, blank procedure results are okay, and DI water or blank water sample results are okay, we can say that the Fusion or Phoenix is not contamination-free. Okay, and just to summarize today, when you're having trouble with your sample results, always check the basic operation of the instrument first. And chances are the root cause of that problem will be found in one of the areas we covered in today's presentation. It's actually not a bad idea to be proactive and actually check these areas before you start a long run of important samples. It doesn't take a long time to do leak checks, check your liquid transfers and the quality of the liquids volumes pulled into the syringe, check your baseline, and run a few cleaning procedures and blank vial or blank water vials to check the counts from those. So check the basics first. That is going to conclude our presentation today. I apologize for running over our allotted period. We will be available, Tom Rohrkemper will be available to answer questions. And additionally, after the presentation today, if you have questions, contact us in technical support at the numbers and email address on the screen. Thank you, everyone, for attending.
Thank you, guys. Tom Rohrkemper is on the chat session. I know he's handled a lot of calls during the webinar, so we appreciate that, and hopefully he was able to answer them. If there's any questions that were not addressed, feel free to email us or type them in now. We'll stay on for a few more minutes. And I just wanted to reiterate that this webinar recording will be available online in the next couple days. And I'd like to thank Steve. This was a very, very informative webinar, and I know it was long, but it was great information for all of you to gain from him. So we thank you, and feel free to type your questions.